All right, hello and welcome back. So this is part 2 of the using the maximum work theorem with chemical work ALEKS topic. I did make a more in-depth part 1 video with a different instance, a different example. I do want to talk about this glucose example though, but I'm going to go through it probably a little bit quicker. If after watching this one you still need some help, then definitely check out that part 1 video. Okay, so in the other video, we talked about this concept of the maximum work theorem, where the maximum amount of work that can be done is going to be related to the amount of work that's released. So in this case, for this glucose example, essentially what we're given here and what we're told is that the body is going to, combust glucose, is basically going to react glucose to produce energy, right? So this negative delta G here indicates that when we, react 1 mole of glucose, we get out this amount of energy, free energy, to then go do work on something else, and that something else in this case is going to be the assembly of a protein. So here, we're going to assemble this protein that has 45 amino acids, and we're told that the energy of formation for forming 1 peptide bond joining 1 amino acid to another is 21 kilojoules per mole. And the other thing that we need to keep in mind here is that for this protein that we're dealing with in this problem, there's going to be 44, right? 45 amino acids, 44 of these peptide bonds created. So right off the bat, we could sort of say 21 kilojoules per mole times 44, of these amino acids, of these peptide bonds, I guess I should say, is going to equal 924 kilojoules per mole. And this is going to be for, 1 full protein. So, we're given this information for 1 bond in our protein. We're going to need to do that 44 times. So maybe I should write 44 bonds here. This is going to be the amount of energy it takes to form 1 mole of the full protein. So I'm sure in all these cases, we're going to have to do a quick little calculation like that. And then that's going to be sort of what we apply the energy that we have up here to start forming that protein. Okay, so let's sort of unpack the rest of this. So we're told that we have 300 milligrams of glucose that's going to combust. So that's going to be, this right here, 300 milligrams. If we know how much, mass that is, we can convert that to moles. And then if we convert that to moles, then we can figure out how much free energy we'll have to then apply to this assembly of the protein. So let's go ahead and do this. 300 milligrams times 1 gram over 1,000 milligrams is going to give us 0.30. So we should put a dot there, right? Grams of C6H12O6 of our glucose. We'll convert that to moles, 0.300 grams of glucose, C6H12O6, times 1 mole over 180.18 grams. So just figuring out how many grams per mole that is, equals 1.665 times 10 to the minus third moles of our glucose. So this is our moles that we have available to do this reaction to get our free energy. So now we're just going to convert this number of moles into the amount of free energy that's going to be released. So 1.665 times 10 to the minus third moles of C6H12O6 times minus 2872 kilojoules, just from up here, divided by 1 mole of C6H12O6. So always a good reminder, check what the coefficient is here, right? So this is telling us 1 mole that reacts gives this amount of energy. So we need to take that into account there. So I paused there just for a second just to make sure that the coefficient here was 1. Otherwise, we'd have to incorporate that here. And then this is going to tell us that we are going to have 4.782 kilojoules of free energy. So, the sign here just indicates that free energy is going to be released. So this minus 4.782, we can really take the absolute value of that. That's the amount of energy that's going to be available to then do work on assembling the protein. So now we really just need to convert this and say 4.782, the amount of energy that's released, the free energy available, is then going to be used to assemble the protein. So we just convert times 1 mole of protein assembly. I'll put protein here. Protein assembly requires 924 kilojoules. And remember that this 924 kilojoules is because we're taking this 21 kilojoules per mole per bond times 44 bonds that we're going to be creating. So then we can do this calculation and end up with 0.005. Two significant figures would be 0.0052 moles of protein. And that is our final answer. So that's what we're looking for. The maximum moles of the protein that can be formed. We can form 0.0052 moles of protein. And then two significant figures is what we're looking for here. So hopefully that makes sense. If there's something, if I went through a little bit too quickly through any of this, definitely check out that other video, that part 1 video that should help answer any of those questions. Thanks so much.